All right, you guys are logged on, ready to go. Yeah.
Wait, we're starting already?
Yeah, guys, the pins on the board. When you look at the speedometer in a moving car, you see that car is what? Where's that needle pointing to? It's pointing to and yeah, there you go. Okay, speed. Josh, you guys, if you look at the study guide I gave you, those 100-something questions, you guys know that that was the first question, right? So we're just going question by question. Okay. And about half of these are going to show up on your actual midterm because I need 50 of those 100-something questions on the midterm. All right, we got points on the board. Yeah. A train travels 7 meters in the first second, 7 meters in the next second, 7 meters again in the next second. What's the acceleration of that train? Zero. Guys, that train's going constant velocity, isn't it? A constant velocity of 7 meters per second. That's zero acceleration. Right. You guys go with zero acceleration. I got Slock, Sarah, Lincoln, Austin, Oswald. Car starts from rest and after 7 seconds picks up to 42 meters per second. What's the acceleration? Might be that middle one right there.
It's actually
Yeah, there you go. 7 times 6 is 42. Right? So you guys know that was the second kinematic equation. All right, Logan, Sarah, Lincoln, Austin, Oswald. Object falls freely in a vacuum.
Probably mine.
Ooh, one winner. Hey, so did you guys see? If you drop something from rest to the top of a cliff, it starts at 0 meters per second. Then after 1 second, it goes to 10 meters per second. And then the next second, it's up to 20 meters per second. And then 30, 40, 50 meters per second. So the velocity is increasing, right? But guys, what could you say happens to the acceleration? Should be constant in a vacuum, right? Constant. Just in this case, 10 meters per second squared on Earth. Yeah. All right, Lincoln getting some points. Yeah. In the absence of air resistance, objects fall at constant. Yeah, acceleration. Yeah. Right. So you just told me like 10 meters per second squared can be constant. Think I have a question on that? Why that's the answer? You guys got it? All right. Slock, Lincoln, Sarah, Logan, Aqua. Objects in free fall. Each second the object falls. Yeah, a larger distance than the previous second. Okay. Like during the first second of falling, will it fall about 5 meters? 1/2 AT squared, right? Right, falls 5 meters. And the next second it picks all the way up to 20 meters, so that's an additional 15 meters. Okay. After 3 seconds, it's fallen a total of 45 meters. Right, just 1/2 AT squared. Yeah. So it's fallen further and further every successive second. Right? Like the gap is spreading out from the previous second. All right. Ball tossed vertically upward, rises, reaches highest point, and falls. During this time, the acceleration. Yeah. As soon as the ball has left your hand to the point right before you catch it, it's always accelerating down. Isn't Earth's gravity always pulling down? Is that okay? Ball throws straight up. At the top of its path, its instantaneous speed is. Yeah, zero speed top. All right. That's Slock, Logan, Austin, Kristen, Oswald. Ball's going straight up at the top of his path. That's acceleration. It's pretty close to. Yeah, how about 9.8 meters per second squared? Right? Remember, from the moment it leaves your hand till the moment you catch it, it's always accelerating down. Okay. You guys good? Logan, Austin, Lincoln, Tristan, Oswald. Car accelerates at 2 meters per second squared. If it starts to rest, how much time to pick up to 20 meters per second? See, it's that middle one, right? Yeah, so 2 times 10 is 20.
I told him it was 10. You did not listen.
Now you guys know on the midterm the numbers could change, right? Like maybe it changes to like 3 and 15 or something. Austin, Lily, Lincoln, Tristan, also really falling object. What was the speedometer? Its speed reading would increase each second by.
It's not cheating. Yeah.
Let's see, it's this column 0, 10, 20, 30, 40, 50. Yeah, it's picking up 10 meters per second every second. Faster, faster. Austin, Lily, Lincoln, Tristan, Oswald. Really falling object starts to rest. After falling for 2 seconds, it will have a speed of about. Speed. Let's see, is that this one right here? Yeah, so 10 times 2. Falls down to the air, it's on an angle. Ooh, projectiles. At the top of the ball's path, its velocity is. What's going on right there? Yeah, try horizontal. All right, swimmers.
Did someone who did?
Ball thrown in the air will never go as far as maybe you would calculate on paper, because why? There's the calculation. It never quite goes that far because.
Oh, that's it. Oh, I think that.
Yeah, that's right. Right. That's the variable we usually ignore in this class. Yeah, like gravity's part of the equation. That's accounted for, but not the aerodynamics. Oh, guys, listen.
Are we 14?
Oh, I thought they were on the intercom. Never mind. All right. Oswald, Lincoln. In the absence of air friction, the horizontal component of a projectile's velocity does not change. Let's see, 40, 40, 40, 40, 40, 40, 40 meters per second.
Oh my god. Wait, I read it wrong.
Yeah, that does not change, right? Lily, Austin, Oswald, Tristan, Lincoln.
Oh, wait, I got it right.
Same time, one ball is thrown horizontally, one ball dropped from the same height. Which hits the ground first? Ooh, the drop ball, one thrown horizontally. Ground first. Yeah, same time, same time. So you can say they both have 0 initial vertical velocity. Vertical component velocity. Lily, Austin, Oswald, Tristan, Lincoln. Airplane flying 40 meters per second north. There's a 30 meters per second eastward crosswind. What's the ground speed? Ooh. Okay, so 40 north, 30 east. Doesn't sound like I'm setting up a what triangle. A what triangle?
I was so bad.
Yeah. Hey guys, how many degrees east of north is the plane going?
I don't know.
37 degrees. You guys remember that? Yeah. Get where the 3, 4, 5 triangles have 37 degree angles on them, don't they? Alright, Lily, Austin, Oswald, Lincoln, Tristan. What's the resultant of 3-unit, 4-unit vector at right angles? Ooh. Yeah. I don't know if you get both of those questions on midterm. Probably one of those show up. Right, 3, 4, 5, right? Pythagoras. Okay, Lily, Oswald, Lincoln, Tristan. When in orbit, a satellite such as the space shuttle. And simply a projectile. So it's being pulled down.
No, we're like this. This is like
Falling around the country.
Yeah, it's not doing like that.
Law of inertia.
I ready, ready. Oh, wait, we'll go with actually great.
It's a true. I'll say it's a true.
I read the song.
Law of inertia.
All of the love. I said over
Cannonball fired into frictionless space. The amount of force required to keep it going.
Oh my god. Yeah.
No force. No force. Okay, Oswald, Lincoln, Tristan, Lily.
I'm really fighting right now.
Force of gravity suddenly stopped acting on the planets. Which path? The colors match. Which?
Oh, I don't know.
Which color?
That's the wrong one.
Yeah, they got a straight line tangent to the front.
Fly string to the sun. Hey.
Gunner, Logan, Lincoln, Tristan, Lily. Sheet of paper can be withdrawn under a container of milk without toppling the. All right. Sure, quickly because.
Oh, no, thank God. Another one got out. Oh, I mean, like.
Oh, wait.
Very hard.
That part doesn't hurt.
And what do we have down here again? We have some plates, no staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
How about that? Yeah. George, Oswald, Kristen, Lincoln, Lily. Force required to maintain an object at constant speed in free space.
You sure thought all the
Oh my god, I didn't go on, go on. I thought I could, so it sounds right, that's the right sound. I think that is.
So what's the force keeping it going? No force.
No force. No force. Austin, George, Kristen, Lincoln, Lily.
I'm moving up.
Acceleration defined as a change in. The change of velocity over change in time. It's a rate change of velocity at the acceleration. So you guys know acceleration is the rate change of velocity.
I did.
But acceleration produced by a net force on an object is.
Is it all the above?
Okay, directly proportional to the net force, inversely proportional to the mass of the object, in the same direction as the net force, all the above.
Probably wrong.
Yeah. Tristan, George, Austin, Lily, Lincoln. Equilibrium. Ooh.
Everything's wrong. I didn't see all
Yeah, okay, no. All those are true. We haven't actually talked much about torque yet, but you know, like a turning moment, like a seesaw or opening a door, turning a wrench. Zero. I'll leave that. Hi, George, Austin, Tristan, Lily, Lincoln.
I lost my tree.
Or with the weight 500 newtons hangs in the middle of the bar, supported by 2 vertical ropes. What's the tension in each rope? No, as long as you're hanging right in the middle. If you're hanging right in the middle.
Probably 0.
Yeah, so 250. Now, guys, what if you weren't hanging in the middle? What if you're like 60% over from one end? Right. Now, in that case, you would need torque to solve that, but we won't get that probably for a little while. We're good there. All right, Logan, George, Austin, Lily, Lincoln. Friction is a force that always acts.
I just look for the word opposite.
Yeah, opposite of the motion. Opposite of the motion. Hey, look up. Here, I got a side question for you guys. Because you guys know, say if I give this a push, it eventually slows down. It's friction slowing it down. But what about this? What if the car starts at rest and I get the car moving forward that way? Guys, what if there's no friction at all between the tires of the road? What does the car do? Just stays in place, right? It's kind of stuck. Like if you were in a bunch of like ice or mud. What force actually allows the car to propel forward? The friction between the tires of the road. Wait a minute. If the car goes forward, I thought friction always opposed motion. Let's look at the underside of the wheel. Is the underside of the wheel actually turning like backwards to the motion of the car? Logan, George, Austin, Lily, Lincoln. What is the maximal resultant possible from 2 newtons and 8 newtons? Maximum. Yeah, you just have them. They're all in the same direction. Hi, George, Logan, Austin, Lily, and Lincoln. What is the tension in each of the 3 ropes at 120 degrees? So the lantern weighs 100 newtons. All right, we're looking at these 3 ropes at 120 degrees.
Oh wait, I'm stupid. It's stupid.
I didn't see it.
Yeah. Oh, whoa. We got that. Okay. All right. Let's over here. Hold on. Get the guy with the phone. Okay, so here's a down force of 100 newtons. Now, guys, if it's equilibrium, the sum of the forces has to be what? Yeah, zero newtons. Okay. These were all at 120 degrees, so keep that pretty close. So probably about like this, about like this, something like that. Okay. Oh, could you break these into components? Let's see. Well, let's put some angles on here first. If this is 120 degrees and this is 120 and this is 120, they're all 120 degrees. Okay. What is this angle right here? Yeah, I think that would be yeah, 60 degrees. Okay, because it's half of this full thing, right? So 60 degrees. Okay. What is what if I introduce an x-axis? Here's an x-axis. What is this angle right here? Huh? What?
60?
Yeah, 30. Yeah, 30.
90. Come on, guys.
Now, okay. So I've got this Cartesian system that's horizontal and vertical. I've got 100 newtons pull down straight vertical. See, I bet I could split these into components. Now, whether you go over first and then up or up first and then over, it doesn't really matter because this is just we're just breaking them into components. Guys, does this have to pull right as much as this pulls left?
Yes.
Yeah, because that would satisfy this condition in the x-axis. Throw a little subscript x there, right? They cancel out right, left. Okay. What about up and down? Do these two collectively pull up as much as this 100 newtons is pulling down? So how much magnitude does this upward have to be? Yeah, 50 over here, and 50 over here. Now, because these are not the full forces; these are just the vertical components of these tensions. They will call us. Well, I'll just call it T for tension. And you guys do see by symmetry that the left tension and the right tension would be the same by symmetry. Right? So I just call it T. Right? Now, well, now what? Hey, can you guys think of a trigonometry relationship you could use to solve the rest of this? Like playing out 30 degrees, and here's the opposite, and here's the hypotenuse. Okay. Guys, what trig relationship connects opposite to hypotenuse? Yeah, that's sine. Yeah. So sine at 30 degrees. Could that be 50 newtons divided by the tension? Is that okay? We got both like these. T sine 30 degrees. It's 50. Oh, guys, what is sine at 30 degrees? 1/2. 1/2.
Of course,
There you go. Whole thing, right? Or you could have said by radial symmetry, since all these three ropes are 120 degrees from each other. Right? Okay, what if you change the story? Here, maybe this is easier. What if it's three friends playing tug of war on a big field? We're up on a helicopter, looking straight down on these three friends. I'm pulling, and the center's not really moving anywhere. Okay. Does it matter how I change the orientation? What if I orient it like this? Okay. Is it still 100, 100, 100? Yeah, still 100, 100, 100. Yeah. Okay. All the angles are the same. So all the dimensions have to be the same. Alright. Yeah. Which has more mass, a kilogram of feathers? Yeah. Yeah. Hey, mass. 1 kilogram. Someone do it. Someone.
I saw the question on.
Maybe it's a question. Let's see. All right. Accelerations are produced by.
No. And then I was taking this. Whatever. Turn me into a big man. Turn me into a big man. And I don't have a plan. I don't have a plan.
Yeah, that doesn't make sense.
Yeah.
All right, so Newton's second law, you guys know forces produce accelerations. All right, guys, George, Logan, Austin, Lily, Lincoln. How does acceleration of an object change in relation to its mass? Like if you push something that's more and more massive, the acceleration becomes. Yeah, so inverse proportion. Here, give guys a visual over here. Suppose I have this versus this. It's the same force of both of them. So there's the same force, different masses, different accelerations. Oh, Logan, George, Austin, Lily, Lincoln. When an object reaches terminal velocity, its acceleration is. Ooh. What's the acceleration at terminal velocity? Yeah, no acceleration. Right. But guys, to have that, can that happen can that happen in a vacuum? Who thinks that can happen in a vacuum? Nobody says that, right? So you have to have air drag to make that happen, right? You have to have some kind of air drag. Logan, George, Austin, Lily, Lincoln. A book weighs 4 newtons. When held at rest in your hands, what's the net force on the book? It looks a lot like this. Weight down, normal force up. What's the net force? Guys, yeah, as soon as you see at rest, what's the net force of anything at rest? Yeah, 0. All the forces cancel out. Yeah. Girl pulls on a 10-kilogram wagon with, let's say, a net force of 20 newtons. What's the acceleration? See, 20 goes here, 10 goes here. Yeah. Everybody wins. Yeah. Gutter, George, Lincoln, Austin, Lily. Oh man, it's a tight race. Constant force produces a constant.
That was easy.
It's both.
Acceleration. Constant net force, right? Nice. Austin, Lily, Lincoln. Suppose the force of friction on a sliding object is 35 newtons. What's the force required to maintain constant velocity? Ooh. So if this is 35 newtons, you want constant velocity, this force has to be 35 newtons. Yeah. All right. You guys get there. Schwab, George, Austin, Lily, Lincoln. And for the win! Aunt Benny throws one rock and drops another. The acceleration of the thrown rock is what compared to the drop rock? Let's say after it leaves her hand. After it leaves her hand. Same. All right. See who won Kahoot day 1. We got with the bronze, Austin, with the silver, Lily, and the gold, Lincoln.